1 second here. Okay, so this is a redo of the last video. So let's see if this will work. So I'm going to take a look at the functions, and we're going to be looking at transformations. So initially we're going to be looking at to see how the graph of f of x changes if we add c to inside the parentheses, and outside the parentheses. So let's see how this is going to work. First off, if we have y equals f of x plus c, how does that change the graph of f of x? Well, one way to think about it is you're adding c to all the x values, so the x-axis is shifting to the right. However, that means the graph itself looks like it's shifting to the left. So the way to graph f of x plus c is to go left c units. That's true if c is positive, by the way. Similarly, if you have f of x minus c, and well, first off, if you're given the graph of f of x and you want the graph of f of x minus c, and c is positive, you want to shift to the right by c to get the graph. Okay, and so what happens if the c is outside the parentheses? Well, that means that you're adding c to all the y values, right? So what's going to happen to your picture then? That means all your y's are shifted up, so therefore the graph is also shifted up by c units. So when they're inside the parentheses, it's kind of the opposite the way you might think it should go. But when they're outside the parentheses, it's just the way you think it should go. So similarly then, if you have f of x minus c, you're going to shift down by c units. Okay. Now, it's a little more complicated when you're multiplying the x-axis by c, because if c, for example, is larger than 1, like if it's, say c is 2, what does 2x do to the x-axis? The x-axis gets stretched by 2, right? Well, if you're outside of the x-axis and you're looking at the graph, it looks like the graph has shrunk vertically or horizontally by 1/2. Okay, and so to get the graph of f of 2x from the graph of f of x, it shrunk horizontally by 1/2. Okay, now if c is already less than 1, so if c was like 1/2 times x, what does 1/2 times x do to the x-axis? It shrinks the x-axis. So if you're looking at the graph of f, the graph of f is actually being expanded by 2. Okay, so again, if c was 1/2, to get the graph of f of 1/2 x, you would have to expand the graph horizontally by 2. If c is equal to -1, that's a special case, right? Because now what happens if your function, you could think of it as being flipped over the x-axis, and so it's not translated over the x-axis. It's actually, there's a mirror image across the y-axis. Okay, and we're going to see that in just a second. If I'm going to just look at this case, the c times f of x, where c is greater than 1, then you're stretching the graph of f by c vertically. If c is less than 1, then you're shrinking the graph of f vertically. And if c is -1, you're flipping the graph of f around the x-axis. This is a lot of stuff to keep in mind. Let's take a look at a picture. That's the easiest way to think about it. So here's the graph of f of x, and if you're adding the c outside the parentheses, that's shifting up. Outside the parentheses, shifting down. This, by the way, is all true if c is greater than 0, this graph here. Then you're shifting left, right, if you have f of x plus c inside the parentheses. If x minus c is inside the parentheses, you're shifting to the right by c. So inside the parentheses, things behave the opposite the way you think it might be, but outside the parentheses, it behaves just like you think it should. Good. Okay, here's what happens in the case where we have the c on the outside. So if c is bigger than 1, then the graph is pulled. By the way, if the graph intercepted the x-axis here, the pulling would not change those points, right? So if this point right here along the x-axis were stuck on the graph there, and you were trying to find like 2 times f of x, then you would just pull everything up, but the zeros would remain the same. Okay, and then if c is greater than 1 and we're multiplying by 1 over c, we're shrinking. And then if we have f of minus x, notice that this is a mirror image across the y-axis. And then if we have the negative sign outside, we're rotating or taking a mirror image across the x-axis. Good. So you can play around with these. They're kind of fun to take a look at. Let's do one more. This is the graph of x squared here on the left. And over on the right, I've translated the graph. So let's see, what was the graph doing here? We shifted backwards 3 and up 1. So if this graph is x squared, what would the formula be for the graph on the right? Did you get a chance to think about it? Did you get the right answer? Excellent. All right. So how about composition? If f and g are 2 functions, define the composition as you're sticking one function inside of another. So f composed with g means that you're sticking g inside of f, or g composed with f. So did everybody catch how I'm saying this with these words? This is g composed with f is g of f of x. Okay. So if f is x squared plus 1 and g is 1 over x, let's compute f composed with g and g composed with f. So first off, f composed with g. So I start with g, the 1 over x, and I stick it in for x in the formula for f. And I get, what? 1 squared over x squared plus 1, and then 1 squared is just 1, so I simplify that a little bit. Good. How about g composed with f? What's that going to be? G is 1 over x. If I stick f in for x, I would have 1 over x squared. Good. And we can also play games. We could do f composed with f, g composed with g. Those are kind of fun to try. So f composed with f, we would have in place of this x right here, right, in the f of x, we would stick x squared plus 1. Right, and so we get that interesting situation. And g composed with g, 1 over x, the operations kind of undo each other, so you end up with x. And we could go backwards as well. Suppose I give you this expression right here, and I say I want to write this as a function composition of 3 functions. How can I do that? Well, the easiest way to do that is to think about how you would compute this on a calculator. So on an old-fashioned calculator, I should say. So suppose that we would put in the x first, right? Then we would compute the x squared. That's function 1. What do you do with that number? You add 2. That's function 2. And then finally, what do you do to that number once you've computed it? You compute the cube root. That's function 3. So what we're saying then is that h is x squared, g is 2 plus x, and then f is the cube root of x. Now I should say that there are multiple ways of doing this. You could also say that h is equal to 1 plus x squared. Then what would g be? Did you say 1 plus x? I bet you did. And then h of x is the cube root of x. Okay, good. So there are multiple ways of computing that. Okay, so we're going towards the idea of a functional inverse, and so before we do a function inverse, we need to understand what it means for a function to be one-to-one. So a function is said to be one-to-one if every x maps onto a unique y. That means if you have 2 outputs from your function and they are different, let me say that a different way. whenever x1 is not equal to x2, if you have two different inputs, they must map to two different outputs. Did everybody catch that? If I have two different inputs to my function, they must produce two different outputs. Okay, therefore, for example, if x1 is 1 and x2 is 2, they couldn't both map to, say, 1. So what does this mean geometrically? What this means geometrically, if I pick a y value, then I shouldn't be able to the horizontal line should not intersect the curve at more than one point. The parabola, for example, if I was at the point 1, which x values give me a function that's x squared equal to 1? Well, x could be plus 1 on this side or minus 1 on this side. So this function right here is an example of a function that is not currently one-to-one. Of course, the way to make it one-to-one is to just disregard one of the two halves of the parabola. So a typical way of constructing the quadratics, or the x squared, so that it is invertible, is to just use the x values that are positive. In that case, you get rid of this negative half, and then the function is one-to-one. Oops. How about the next function? This one? This is a cubic function. Is that one-to-one? It is one-to-one. Good. So a function is one-to-one, by the way, maybe I'll say this real quick. Geometrically, the function is one-to-one if it passes the horizontal line test. What is the horizontal line test? Any horizontal line that passes through the graph must pass at most once. It cannot pass, or it cannot intersect at more than one point. If it does, then it's not one-to-one. Okay, so now function is one-to-one with domain A and range B. Then the inverse function is denoted by f inverse. So that's how we read it. F inverse. It has domain B and range A. Notice that if f maps A to B, then f inverse takes B and goes back to A, and is defined by f of f inverse is just x, and f inverse of f is just x. So what does that mean? It's probably easiest to see this way. If f maps x to y, then f inverse takes y back to x. That's what the inverse function does. It undoes the operation. Whatever the operation was originally, f inverse will undo it and take you back to the original. Just a quick notation, f to the minus 1 power is not 1 over f of x. What is this called? F inverse. So if I want the reciprocal function here, usually I'll put parentheses around the f, but I'll make that really clear. If you're ever not sure, just ask. Okay, so here's an example of a function. It's given to you pointwise, the x's and y's. How would you compute the inverse? Well, we just flip the table so that the new inputs are the old outputs, right? So now 2 will map to minus 1, 1 goes to 0, 0 goes to 1, minus 1 goes to 2. So forming the inverse from a table is really easy. All you do is flip the table. Similarly, what happens, this is a good chance to see why if one-to-one is really important. So in this table, suppose that my y values, I have two y values here of 1. So minus 1 goes to 1, 0 goes to 1, 1 goes to 0, 2 goes to minus 1. Why is this a problem when you take the inverse? Do you see it? This is going to be a big problem here on the right. Why? This table on the right corresponds to something that is not a function, because the point 1 is going to two different outputs. So this table right here is not a function. So what we've just concluded is a function must be one-to-one in order for the inverse to be a function. Okay, so let me say that again. A function must be one-to-one in order for the inverse to be a function. Good. If the function, okay, I just repeated myself there. How do you find the inverse graphically? You reflect the curve across the line y equals x. That is how you change the role of x and y. And so we're going to take a look at a couple of examples. Algebraically, oops, I see I have a typo. This should be to find the inverse algebraically, swap x and y and solve for y. We'll do that as well in just a second. So here's my quadratic function, and I said that this was not one-to-one. If I reflect the parabola across the line y equals x, this blue line here, I get this green then blue sideways parabola. What's the trouble with the sideways parabola? Well, there's nothing wrong with it except that it's not a function, right? And so we typically want our inverse to be a function. So how do we get around that? Well, we break up the parabola into two pieces. The piece on the left here is using only the positive values of x to create the parabola. And so this green curve now is the inverse. Can you guess what that is? That curve is the square root of x. On the other hand, if I choose to have only the negative values of x and my parabola, then the inverse function turns out to be minus the square root of x. Okay, and so these two functions separately are inverse functions. So depending on the domain, you can get different inverses, right? If the function is not one-to-one. Good. Let's do an algebraic example. F of x is x plus 1 over x minus 2. Find f inverse. So what do? Do you remember this from pre-calculus? Swap x and y, solve for y. That's typically how it's remembered. So swap x and y, solve for y. And if I do that, then we just do a little bit of algebra. I need to isolate y. So the best way to do that is to multiply both sides by the y minus 2 first to clear the denominator. And now I've got this multiplication. Don't divide again. We need to multiply this out on the left so that we can get the x and the y, so we can separate the x and y again. And now that once I've multiplied it through, I can see now I can get all my y's together. And so I'll bring the 1 over to the left and the xy over to the right, and what do I get? I get minus 2x plus 1 equals y minus xy, and now I can factor the right hand side to isolate y, and then I can divide. Now you could leave your answer like this. This is fine. Sometimes the mathematician in me wants us to keep going to get it aesthetically pleasing. So I don't know, is this more aesthetically pleasing than the other one? What I did was multiply by -1 over -1. It's nice to have an aesthetically pleasing expression. Okay, so that's it. I think I've probably gone over time. So what we've done today is talk about function composition and function inverses. And now we know how to find an inverse geometrically and algebraically. Okay, now let's see if I can figure out how to end the tape.